lesson 50 is standing waves, and as you can see from my smartboard page, I love standing waves. I've got tons of videos that I show for standing waves. It's really important. I know I keep saying this, but really important that you go onto YouTube and watch some videos on standing waves. I'd recommend this one, Professor Dave, Standing Waves and Harmonics, but there's a whole bunch of really good videos, not only explaining standing waves, but giving examples, because they're super important in the universe that we live in. So watch this video, and then, there we go, and then let's take a look at this very quickly. So here's something that has is fixed on both ends, and I'm just going to send a pulse over, and you can see the pulse goes back and forth, and it inverts because the clamp over there will not move. So that's just one pulse. But if I send another pulse, let's say I send a pulse here, then those two pulses interact with one another, and they create constructive and destructive interference. So remember, when a crest meets a crest, you get constructive interference. When a crest meets a trough, you get destructive interference. And if the amplitude of the crest and the trough are the same thing, they cancel each other out. So now I'm going to quickly change this to oscillating, and we get this. All right, and as you can see, at times, you can see that the wave appears like right there, and then it completely disappears. If you look at one of the green dots here, at times they sit on this line and don't move, and that's a standing wave. Okay, I'm gonna go back to the lesson now. Stop. That's a standing wave. So if you watch the videos, about a few videos about standing waves, then you'll understand this. I won't need to explain in great detail, but I'll try. And the reason I wanted you to watch the videos is because it's just difficult to explain in a smartboard presentation. It's much better if I'm in front of you and we've got a slinky and you can see how a standing wave works really well. But here we go. It says standing waves are just an extension of the concepts of resonance, waves at boundaries, and superpositioning. So it's basically the wave, a pulse goes over to one side, bounces back, and then, as you can see here, a crest meets a crest, and so you get a supercrest. And here, a trough is meeting a trough, so you get a super trough, and in the middle, and we call that a node, in the middle you get where a crest meets a trough, and you get completely destructive interference. So this is the constructive interference. Right here, right at the top there, and right there. And the constructive interference produces what we call antinodes. So the antinodes are where a crest meets a crest or a trough meets a trough, and you get constructive interference. Where a crest meets a trough, and they're identical in magnitude, you get complete destructive interference. So that is destructive. Nice spelling of destructive. And as said, we call that a node. And so in this diagram, there are actually three nodes, because there's a node right here, there's a node here, and there's a node there. This is a fixed string, like a guitar string or a violin string, for example. This is how they would vibrate. They would create nodes on either end, and then some nodes in between. Or you don't need a node in between. If you just get a string, attach it from here to here, and then just swing that string so it's going up and down like that, then that is the shortest form of a standing wave, and it's just getting a little ahead of ourselves. That represents half a wavelength, whereas this whole thing here represents one wavelength. Okay, we'll more on that later, so don't get too confused. So here we go. So you see that at 1 second, and then you see this here, and what it appears to look like is that. So you just get a wave that looks like it's just going The particles on the wave, this is a particle on the wave, is just going ding, 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 like that. And this particle here is not moving. And again, if we had a slinky and you saw this firsthand, you'd say, oh yeah, that is very, very obvious. So in this case, we have 2 antinodes and 3 nodes. And is that it? Is that the whole lesson? That's really it. That is the whole lesson. That's the whole lesson. Let's just do a couple of examples here, because as I said, you can have, if you have a string that's fixed on both ends, like a guitar string, then you can make a standing wave just by having that string go up and down like this, and that represents half of a wavelength, right? Because there's 1/2. And that would be the other half. So that represents half a wavelength. It has 1 antinode right here and 2 nodes, there and there. Node, node, antinode in the middle. So you can have, if you have an object that has 2 fixed ends, then you can, the shortest wavelength you can have that will create a standing wave is half a wavelength. Then you go on to the next one, which is going to be 1 wavelength, 1 full wavelength. And in this one, we have, how many nodes do we have? Let's do all the nodes in blue. 1, 2, 3. So in this example, we have 3 nodes. And how many antinodes do we have? 1, 2. 2 antinodes. Okay, and then you can, if you just vibrate the string at a faster frequency, and you have to be very specific. The frequency and the length of the spring or the length of the string are very important. So if you continue vibrating it faster, you'll get to the next one, which would be, well, you can probably guess if the first one is a half and the second one is at 1 wavelength, the next one is probably 1.5 wavelengths. 1, 2, 3. There we go. There's 1.5 lengths. What has to happen here is you have to have, since it's a fixed string that's has 2 fixed endings, you have to have a node here and you have to have a node there. So how many nodes does this one have? This one has 1, 2, 3, 4 nodes. How many antinodes? Oops, I did it in the wrong color. That's okay. 1, 2, 3. So you can start to see the pattern here. This one has 4 nodes and 3 antinodes. And the next one is going to be 2 wavelengths, and then 2.5 wavelengths, and so on. So that's how you can create a standing wave if both of these are fixed, like a guitar string. And the reason that I'm emphasizing that is because in the next lesson, resonating air columns, we're going to talk about standing waves that occur where there is not a fixed end at both ends. For example, when you play the trumpet or the clarinet or the flute, then those they don't create standing waves that have a fixed end on both sides. One of them is open, and in some cases, both of them are open. All right, more on that for resonating air columns. But yeah, please go onto YouTube and watch some videos on standing waves. This is actually a standing wave in the Bow River that people routinely surf on. So you can surf on a standing wave because the wave does not move closer to the shore. It stays in one position. So you can get on that wave and you can surf there until you starve to death. All right, we'll see you for resonating air columns.